Good evening, everyone, and welcome to the Droning Professor. Tonight we're going to learn about the strange tech Vikings used to see without light. So as you make yourselves comfortable, please take a moment to let us know where you're listening from and feel free to subscribe. Now, as always, take a moment for some deep breaths, letting your mind and body relax for a good night of sleep. Good evening, everyone. Tonight we're going to talk about something that sounds like it came straight out of a fantasy novel, but is actually rooted in historical accounts and modern scientific investigation. We're going to explore how the Vikings, those seafaring warriors and traders who terrorized and fascinated medieval Europe, might have navigated across vast stretches of open ocean using a piece of technology so simple, so elegant, and so weird that when scientists first started taking it seriously, a lot of people thought they were joking. I'm talking about the sunstone, a crystal that supposedly allowed Norse navigators to find the sun even when it was hidden behind clouds, fog, or even below the horizon. Now, before we dive into the science and history, let me set the stage for why this matters. The Vikings didn't just hop in their long ships and sail around the coast of Scandinavia. No. These ambitious maritime adventurers crossed the North Atlantic Ocean. They settled Iceland starting around 874. They colonized Greenland around 985. And they reached North America, specifically what they called Vinland, around 1000. We have archaeological evidence of a Viking settlement at Lonsog's Meadows in Newfoundland to prove it. These journeys weren't short coastal hops. We're talking about sailing from Norway to Iceland, which is roughly 620 miles, or from Iceland to Greenland, another 550 miles or so, across open ocean where you can't see land for days. Here's the problem. The Vikings didn't have magnetic compasses. The compass as a navigation tool didn't show up in Europe until the late 12th or early 13th century, well after the Viking Age had ended. The Viking Age is generally considered to span from about 793, with the raid on Lindisfarne, to 1066, with the Battle of Stamford Bridge. So how did they do it? How did they navigate across featureless ocean where there are no landmarks, where storms can blow you off course, and where the weather in the North Atlantic is notoriously terrible? The answer, according to several Icelandic sagas, might be something called a solarstein, which translates directly to sunstone. Now, sagas are these incredible narrative works of medieval Icelandic literature, and they mention the sunstone in a few places. The most famous reference comes from the saga of King Olaf, which was written down in the 13th century but describes events from the 11th century. In this saga, the weather is overcast and snowing, and King Olaf uses a sunstone to locate the position of the sun despite it being completely hidden from view. The saga describes him holding up the stone, looking at it, and then determining where the sun was in the sky. Based on this information, he could figure out directions and navigate. For a long time, historians and scientists kind of shrugged at this. It seemed like medieval fantasy, like magic crystals from a role-playing game. But then people started thinking about it more seriously, and they realized something. There are crystals found in nature that have very specific optical properties, properties that could theoretically be used to locate the sun even under overcast skies. And the Vikings absolutely had access to these crystals. They had the materials, they had the need, and they had the maritime tradition that would have made developing such a technology not just possible but necessary. So let's talk about the science behind this, because it's genuinely fascinating. The key concept here is something called polarization of light. Now, don't worry, I'm not going to make you relive your physics nightmares. I'm going to explain this in a way that actually makes sense. Light is an electromagnetic wave, and when light waves travel, they oscillate in different directions. Unpolarized light, like the light that comes directly from the sun, oscillates in all directions perpendicular to the direction it's traveling. Think of it like a jump rope being shaken in all possible directions at once. Polarized light, on the other hand, oscillates primarily in one direction. If unpolarized light is a jump rope shaking every which way, polarized light is a jump rope shaking only up and down, or only side to side. Here's where it gets interesting. When sunlight enters Earth's atmosphere, it interacts with air molecules and gets scattered. This scattering process, called Rayleigh scattering, is why the sky is blue, but it also polarizes the light. The scattered light becomes partially polarized, and the degree and direction of polarization creates a pattern across the entire sky. This pattern is related to the position of the sun. Even if the sun itself is hidden behind clouds or below the horizon, the polarization pattern remains detectable in the visible portions of the sky. It's like the sun leaves a fingerprint on the sky that you can read if you have the right tool. This polarization pattern forms something that scientists call the celestial polarization pattern. At a 90-degree angle from the sun, the polarization is at its strongest. The light is most polarized perpendicular to the sun's position. As you move toward or away from the sun, the polarization weakens. There's also something called the Rayleigh sky, which describes how this pattern extends across the entire celestial dome. The critical point is this: if you can detect the direction of polarization in one part of the sky, you can use that information to calculate where the sun is, even if you can't see the sun itself. Now, certain crystals have a property called birefringence, also known as double refraction. When light passes through a birefringent crystal, it splits into two rays that travel at different speeds and exit the crystal slightly offset from each other. The key is that these two rays are polarized perpendicular to each other. If you look through such a crystal at a light source, you might see two images. The relative brightness of these two images depends on how the crystal is oriented relative to the polarization of the incoming light. If you rotate the crystal, the two images will change in brightness relative to each other. When the two images have equal brightness, you know that the crystal is oriented at a specific angle to the polarization direction of the light. So, which crystals have this property and were available to the Vikings? There are three main candidates that researchers have focused on. The first is calcite, which is a calcium carbonate crystal, also known as Iceland spar, because it was found in, you guessed it, Iceland. Calcite exhibits very strong birefringence. If you place a clear piece of calcite over text, you'll see two images of every letter. It's a striking visual effect. The Vikings definitely had access to calcite. Iceland is geologically active, and calcite deposits are common there. It's also transparent enough to see through, which is important if you're trying to use it as an optical instrument. The second candidate is cordierite, also known as iolite or water sapphire. Cordierite is a magnesium iron aluminum cyclosilicate, and it's strongly pleochroic, meaning it appears different colors when viewed from different angles. When you look through cordierite at polarized light and rotate it, the crystal changes color dramatically, from blue to yellow to almost clear. This color change is very obvious and could serve as a clear indicator of polarization direction. Cordierite can be found in Scandinavia, particularly in Norway, so Vikings would have had access to it. The third candidate is tourmaline, a complex borosilicate mineral. Tourmaline also exhibits pleochroism, though not as dramatically as cordierite. It's been found in Viking Age contexts, so we know they had it. Tourmaline changes from darker to lighter as you rotate it relative to polarized light. Now, here's where the story gets really interesting. In 2013, a research team made a discovery that brought all of this from the realm of speculation into something much more concrete. A shipwreck was found off the coast of Alderney in the Channel Islands. The ship was identified as La Cordelière, which sank in 1542, well after the Viking Age, but still before the widespread use of reliable magnetic compasses. Among the navigational instruments recovered from the wreck was a piece of calcite crystal found close to other navigation devices. This was the first archaeological evidence that calcite crystals were actually used for navigation by medieval sailors. The crystal from the wreck was analyzed, and researchers conducted experiments to see if it could have been used as a navigation tool in the way the sagas described. They found that yes, it absolutely could have been. They tested whether the crystal could be used to determine the sun's position under various conditions, including twilight and overcast skies. The results were promising. The calcite crystal could indeed be used to find the sun's location by detecting the polarization pattern in the sky. But let's get practical here. How would a Viking actually use this thing? It's not like there was an instruction manual carved into a rune stone. Based on the experiments and the historical accounts, here's what researchers think the process might have looked like. First, the navigator would hold the crystal up to the sky, looking through it in a direction away from where they think the sun might be. Remember, they're trying to find the sun, so they don't know exactly where it is. They would rotate the crystal while looking at the sky through it. As they rotate, they would watch for either the relative brightness of the double images in calcite, the color change in cordierite, or the brightness change in tourmaline. When the indicator hit a specific point, like equal brightness of the double images or maximum color change, they would note the orientation of the crystal. This tells them the direction of polarization in that part of the sky. Now here's the clever part. They would repeat this process at multiple points in the sky, creating a sort of mental map of the polarization pattern. The Vikings were incredible observers of nature. They had to be to survive. They could read currents, wave patterns, whale migration routes, and bird behavior. Reading a polarization pattern would have been right in their wheelhouse. Once they had measurements from several points, they could triangulate the sun's position. The point in the sky where all the polarization directions intersect at 90 degrees is where the sun is located, even if it's hidden. There's actually an even simpler method that might have been used, especially for maintaining a course rather than finding absolute direction. If you're sailing and you want to maintain a constant bearing relative to the sun, you can use the sunstone to check periodically whether the polarization direction has changed. As long as the polarization pattern remains constant relative to your ship's heading, you know you're still on course. You don't need to calculate the exact position of the sun every time. You just need to verify that your relationship to the sun hasn't changed. Think of it like using the North Star to maintain a northerly heading. You don't need to constantly calculate your exact latitude. You just need to keep that star at the same position relative to your ship. Now you might be thinking, okay, this all sounds very clever, but did it actually work? Could you really navigate across the Atlantic using a magic crystal? Well, researchers have actually tested this. Multiple teams have conducted experiments using replica Viking ships and sunstones to see if this navigation method could have gotten the Vikings where they needed to go. One of the most comprehensive studies was done by a research team that simulated a journey from Norway to Greenland using only sunstone navigation. They factored in typical North Atlantic weather patterns, including cloud cover, fog, and the long twilight periods of high latitudes. Remember, in the summer at high latitudes, the sun barely sets. You get this extended twilight period where the sun is below the horizon but the sky is still illuminated. This is actually when polarization patterns are most pronounced and easiest to detect. The simulation results were impressive. Using sunstone navigation with measurements taken at regular intervals, the simulated Viking ship could have successfully navigated from Norway to Greenland with accuracy comparable to or better than magnetic compass navigation under similar conditions. The key was taking measurements frequently, every few hours during the journey. Each measurement would give a sun position, and over time, these would allow the navigator to maintain course and estimate their position. The margin of error was certainly larger than modern GPS, obviously, but it was more than sufficient to get you from one landmass to another across the Atlantic. Remember, Greenland is a massive island. You don't need pinpoint accuracy. You need to get within 100 miles or so of your target, and then you can use other signs like bird sightings, wave patterns, and eventually visual contact with land to make your final approach. There's another piece of evidence that supports the sunstone theory, and it's written in wood. In 1948, archaeologists discovered a fragment of what appeared to be a navigational instrument in the ruins of a Benedictine convent in Greenland. This artifact, known as the Unartuk disc, dates from around 1100 or so, right at the end of the Viking Age. It's a circular piece of wood with various markings on it. For decades, people weren't sure what it was. Some thought it might be a decorative piece. But in 2013, researchers analyzed it more carefully and concluded that it's a bearing dial, a navigation instrument that would work in conjunction with a sunstone. Here's how it would work. The disc has markings that divide it into directions, sort of like a compass rose. It also has notches and lines that correspond to the sun's path across the sky at different times of year. A navigator would use the sunstone to determine where the sun is, then align the bearing dial with that solar position, and use the markings on the dial to determine cardinal directions and maintain their course. It's a combination of the sunstone's ability to find the sun and the bearing dial's ability to translate that into practical navigation directions. The fact that such an instrument was found in a Norse settlement in Greenland, a place they could only reach by successful ocean navigation, is pretty compelling evidence that they had some sophisticated navigation technology. Now let's talk about the limitations, because nothing is perfect, and certainly not a chunk of crystal. First, the polarization pattern in the sky is most detectable when the sun is relatively high in the sky and when the sky is partially clear. If it's completely overcast with thick cloud cover, the polarization pattern can be significantly weakened or scrambled. However, experiments have shown that even with fairly heavy cloud cover, as long as there's some patch of sky visible, the pattern can still be detected. It's not as easy, and it's not as accurate, but it's still usable. Vikings would have been motivated navigators with a lot of practice. Second, the polarization pattern is weakest when the sun is very close to the horizon or directly overhead. Directly overhead is rarely a problem in the North Atlantic because of the latitude, but the low sun angle during early morning and late evening could be challenging. However, this is somewhat offset by the fact that twilight periods at high latitudes are prolonged, and the polarization pattern is actually quite strong during twilight, because the sun is below the horizon but still illuminating the atmosphere. Third, you need some skill to use this device. It's not like GPS where you just look at a screen and it tells you where you are. You need to understand what you're looking for, how to interpret the changes in the crystal, and how to translate that into navigation information. But the Vikings were professional sailors. They spent their lives on the water. They learned navigation from childhood. They had oral traditions that passed down knowledge from generation to generation. Learning to use a sunstone would have been part of that training. There's also the question of why the sagas don't give us more detailed descriptions of how to use these sunstones. If they were so important, why don't we have instruction manuals? Well, think about it this way. If I asked you to explain how to ride a bicycle in writing, could you do it in a way that someone who had never seen a bicycle could learn from your text alone? Probably not. Some skills are learned by doing and by being shown, not by reading about them. The sagas weren't technical manuals. They were stories. And they mentioned the sunstone in passing because their audience already knew what a sunstone was and how it worked. It would be like a modern story mentioning someone using their phone to navigate. The story doesn't stop to explain how GPS works because the audience already knows. Another interesting angle on this whole thing is the question of magnetic navigation. Why didn't the Vikings use magnetic compasses? Well, as I mentioned earlier, the magnetic compass wasn't used for navigation in Europe until after the Viking Age. But here's something fascinating. The Vikings did know about magnetism. We have evidence that they understood lodestone, which is naturally magnetic iron ore. But in the North Atlantic, magnetic compasses have significant problems. The magnetic North Pole is not at the geographic North Pole. At high latitudes, the difference between magnetic north and true north, called magnetic declination, can be very large and changes depending on where you are. In parts of the North Atlantic, the declination can be 30 degrees or more. If you're using a magnetic compass and you don't correct for this, you'll end up way off course. Even more problematic, at very high latitudes, magnetic field lines point steeply downward into the Earth. This is called magnetic inclination or dip. When this happens, compass needles don't swing freely in a horizontal plane. They want to point down into the ground. This makes them sluggish and unreliable. In fact, magnetic compasses are notoriously problematic near the Arctic Circle. The Vikings were sailing in exactly the regions where magnetic compasses work poorly. So even if they had developed the magnetic compass earlier, it might not have been particularly useful for their specific navigation needs. A sunstone, on the other hand, works based on the sun's position, which is related to true geographic north, not magnetic north. It's not affected by magnetic declination or inclination. In some ways, it's actually a superior navigation tool for high-latitude sailing. Let's talk about some of the mythology and culture around this. The Vikings had a rich mythological tradition, and the sun played an important role in it. In Norse mythology, the sun is personified as the goddess Sol, who drives her chariot across the sky, chased by the wolf Skull. When Ragnarok comes, Skull will finally catch and devour Sol. The sun's daily journey across the sky was sacred and important. For a seafaring people, being able to find the sun even when it was hidden would have seemed almost magical, a way of maintaining that connection to Sol even when she was obscured from view. There's also the practical matter that these sunstones might have been valuable and rare enough to be mentioned in sagas specifically because they were notable items. Not every ship might have had one. They might have been prized possessions of experienced navigators, passed down or traded at high value. In the saga of King Olaf, the sunstone is presented as a special item that the king has access to. It's not described as common equipment. This would make sense if sunstones were valuable pieces of navigation technology that required expertise to use and weren't universally available. Now, I want to address something that sometimes comes up in discussions of Viking navigation. Some people point out that Vikings could also navigate using other methods, observing whale migration, following birds, reading wave patterns, and using dead reckoning based on speed and time. All of this is absolutely true. The Vikings were masters of environmental observation. They used every tool at their disposal. But here's the thing. None of these methods are mutually exclusive with sunstone navigation. In fact, they're complementary. You would use all of them together. Think about it this way. Birds can tell you that land is nearby, but they don't tell you which direction to sail to get from Norway to Iceland when you're in the middle of the ocean with no land in sight. Wave patterns can give you information about distant storms and landmasses, but interpreting them requires you to already have some sense of direction and position. Dead reckoning, estimating your position based on your speed and direction over time, is crucial, but it accumulates error. If you don't have a way to periodically check your bearing against something absolute like the sun's position, you'll drift off course. The sunstone would have been one tool in a comprehensive navigation toolkit. There's also evidence that Vikings used latitude sailing. This is a technique where you sail to the latitude of your destination, then turn and sail east or west along that latitude until you reach your target. To do this, you need to be able to measure latitude, which you can do by measuring the height of the sun at noon or the height of the North Star at night. A sunstone could help with this. By finding the sun even under overcast conditions, you could take solar altitude measurements more frequently, which would let you stay on your target latitude more accurately. This is particularly important when sailing from Norway to Iceland or Iceland to Greenland, where you're trying to hit a relatively narrow target after crossing hundreds of miles of open ocean. Let me paint you a picture of what this might have looked like in practice. It's around 990, and you're a navigator on a Nar, which is a Viking cargo ship, heavier and wider than the famous longships, but better suited for ocean crossings. You're sailing from Iceland to Greenland, carrying settlers and supplies. Your ship is about 54 feet long with a single mast and a square sail. You're carrying livestock, timber, and several dozen people who are risking everything on this journey to a new land. You left the fjords of Iceland several days ago. For the first day, you could still see the peaks of Vatnajökull Glacier behind you. Then it sank below the horizon, and you've been in the open ocean ever since. The North Atlantic in summer, no land in sight. The weather has been overcast, which is typical. Heavy gray clouds, occasional drizzle, and that constant wind that fills your sail but also chills you to the bone even in July. You need to maintain a westward course, slightly north of due west, to account for the drift of currents. If you sail too far north, you'll miss Greenland entirely and end up in the Arctic ice. Too far south, and you'll overshoot and waste precious days finding your way back. Your life and the lives of everyone on this ship depend on holding the right course. Several times a day, you pull out your sunstone. It's a piece of calcite about the size of your palm, wrapped in leather to protect it from the salt spray. You hold it up to the sky, away from where you think the sun might be. You look through it, seeing the double image of clouds and sky. You slowly rotate the crystal, watching the two images change in brightness. They're equal. You note the orientation. You do this at several different points in the sky, building up your mental map. Based on these observations, you determine that the sun is in the southern part of the sky, as it should be at this time of day. You check your bearing dial, a wooden disc with markings, and confirm that your ship's heading is correct. You're still on course for Greenland. Hours later, the clouds break for just a moment, and there's the sun, exactly where your sunstone told you it would be. It's a small confirmation, but it matters. You adjust your heading slightly based on this direct observation, then the clouds close back in, but you're confident. You know where you are, you know where you're going, and you have the tools to get there. Days later, you start seeing signs. First, drift ice, small chunks floating in the water, which means you're approaching Greenland's waters. Then birds, Arctic terns and fulmars, which nest on the Greenland coast. Then finally, through the mist, the dark line of mountains. You've made it. Using nothing but wind, sail, a wooden ship, your knowledge of the sea, and a piece of crystal, you've crossed one of the most dangerous oceans on Earth. That's the magic of the sunstone. Not magic in the fantasy sense, but magic in the sense of human ingenuity taking a natural phenomenon, understanding it, and using it to accomplish something extraordinary. The Vikings didn't have GPS, radar, or engines. What they had was observation, experience, and clever technology that worked with natural principles. Now, there's still debate in the academic community about exactly how widespread sunstone use was and which crystals were most commonly used. Some researchers think calcite was the primary crystal because of its availability in Iceland and its strong birefringence. Others argue for cordierite because of its more obvious color-changing properties, which would be easier to use without extensive training. There's also the possibility that different crystals were used in different regions or time periods, or that different navigators had their preferred tools. What's not really in debate anymore is whether this could have worked. The physics is sound. The materials were available. The Vikings had the need and the expertise, and experimental replications have shown that it's effective. The question now is more about the specific details of implementation rather than whether it was possible at all. I think one reason this story resonates with people is that it shows that our ancestors were far more sophisticated than we sometimes give them credit for. It's easy to look at medieval people and think of them as primitive or superstitious, especially when we read about magic stones in old sagas. But the reality is that the Vikings were solving complex problems using keen observation and scientific principles, even if they didn't call it science. They understood optics well enough to exploit polarization for navigation. That's not primitive. That's brilliant. It also reminds us that there are multiple ways to solve problems. We tend to think of navigation as requiring electronic instruments because that's what we use now. But the Viking solution was elegant in its simplicity. A crystal, the sky, and human observation. No batteries required, no satellites. Nothing that could break down except the crystal itself, and you could always get another one. In some ways, it's a more robust solution than electronic navigation, at least for its specific context. There's a beautiful parallel here with other traditional navigation methods that modern science has validated. Polynesian wayfinding, where navigators from Pacific Islands sailed across thousands of miles of ocean using stick charts, star paths, wave patterns, and observation of birds and fish, was long dismissed as primitive or lucky. Then researchers actually studied it, sailed with traditional navigators, and realized that it's an incredibly sophisticated system that works remarkably well. The same thing has happened with Aboriginal Australian navigation in the desert, Inuit navigation in the Arctic, and now Viking navigation in the North Atlantic. Traditional knowledge isn't superstition. It's usually the result of generations of careful observation and experimentation. Let's talk for a moment about why the sunstone might have been forgotten. After all, if it was such a great navigation tool, why did it disappear? Why aren't we using sunstones today? Well, first, the magnetic compass did eventually arrive in Europe, and once navigators learned how to correct for magnetic declination, it became a very convenient tool. It doesn't require any skill to read a compass beyond knowing which direction is north. You don't need clear sky or any particular conditions. You just look at it and it points north. That simplicity is valuable, especially as maritime trade expanded and more people needed to navigate who didn't have a lifetime of training. Second, the rise of better astronomical instruments like the astrolabe and the sextant gave navigators more accurate ways to determine latitude and longitude. By the age of exploration in the 15th and 16th centuries, navigation was becoming more mathematical, more based on tables and calculations. The sunstone was a tool based on natural observation and interpretation, which didn't fit as well into this new paradigm. Third, and maybe most importantly, the culture that developed the sunstone, the Norse maritime culture of the Viking Age, declined. After the 11th century, the great period of Viking exploration and expansion was over. The Greenland colonies eventually failed, probably due to a combination of climate change, the Little Ice Age beginning around 1300, and economic shifts that made the colonies less viable. Iceland became more focused on fishing and trade within the North Atlantic rather than exploration. The specific knowledge of sunstone navigation might have been passed down for a while, but as fewer people needed it, it would have been lost. This is a pattern we see throughout history. When a technology is no longer necessary, the detailed knowledge of how to use it fades. We have plenty of examples from our own time. How many people today can use a slide rule? That was essential technology for engineers and scientists for decades. But once electronic calculators came along, the skill disappeared in a generation. The sunstone likely followed a similar path. As navigation technology changed and the specific maritime culture that used it declined, the detailed knowledge was lost, leaving us only with tantalizing references and sagas. But here's what I find really exciting about this whole field of research. We're using modern science to rediscover lost technology and validate traditional knowledge. We're using polarimetry, optical physics, computer simulations, and experimental archaeology to understand what the Vikings knew and how they did it. In a way, we're having a conversation across 1,000 years. They left us clues in their stories and artifacts, and we're using our tools to decode those clues and reconstruct their achievements. This research also has practical applications today. Understanding how polarization patterns work in the atmosphere is useful for optical research, atmospheric science, and even animal behavior studies. Many animals, including some birds, fish, and insects, can detect polarized light and use it for navigation. Bees use polarization patterns to navigate from their hive to flowers and back. Some fish use it to navigate in murky water. Birds might use it during migration. By studying how Vikings might have used polarization for navigation, we're also learning about these natural systems and how they work. There's even been some interest in developing modern navigation systems based on polarization detection as a backup to GPS, especially for military applications where GPS might be jammed or unavailable. In a weird twist of history, we might end up coming back to a technology that the Vikings used 1,000 years ago, just with electronic sensors instead of crystals. Before we wrap up, I want to address one more thing. Sometimes people ask, if the Vikings were such great navigators, why did the Greenland colonies fail? Doesn't that suggest their navigation technology wasn't that good? The failure of the Norse Greenland colonies, which were abandoned by around 1500, had nothing to do with navigation technology. The colonies failed because of climate change, specifically the onset of the Little Ice Age, which made farming increasingly difficult. They also became economically isolated as trade patterns shifted, and the resources Greenland could offer, like walrus ivory, became less valuable in European markets. And there's evidence of conflict with the indigenous Thule people who were expanding into Greenland at the same time. Navigation wasn't the problem. The colonies failed because the environment and economy that supported them collapsed. In fact, the very existence of those colonies, for over 400 years, from around 985 to around 1500, is testament to how good Viking navigation was. They maintained contact with Iceland and Norway across hundreds of miles of open ocean for centuries. That requires reliable navigation technology. So what's the final verdict on Viking sunstones? Based on the historical references, the archaeological evidence, the experimental studies, and the physics involved, the consensus among researchers is that yes, Vikings likely did use crystals with polarizing properties as navigation aids. The most likely candidate is calcite, though cordierite and possibly tourmaline might have also been used. These sunstones would have been used in conjunction with other navigation methods like dead reckoning, latitude sailing, and observation of natural signs. They wouldn't have been magic devices that allowed perfect navigation in all conditions, but they would have been effective tools that significantly improved a navigator's ability to maintain course and determine position during transoceanic voyages. It's a reminder that our ancestors were clever, observant, and capable of sophisticated technology, even if that technology was different from what we use today. The Vikings looked at the natural world, noticed that light behaves differently when scattered through the atmosphere, realized that certain crystals could detect those differences, and figured out how to use that knowledge to sail across oceans. That's not just impressive, it's inspiring, and it makes you wonder what other lost technologies are waiting to be rediscovered, what other references in old texts that we've dismissed as fantasy or myth might actually be descriptions of real, working technology. History is full of surprises, and the sunstone is one of the best. A piece of crystal that let the Vikings find the sun even in darkness, that let them navigate across the North Atlantic to discover new lands, and that we're only now, 1,000 years later, beginning to fully understand and appreciate. That's the beauty of this kind of historical research. We're not just learning about the past, we're learning about human ingenuity, about how people solve problems with the tools and knowledge available to them, and about how the scientific principles underlying the natural world are constant across time. The Vikings didn't know about electromagnetic waves or Rayleigh scattering, but they knew that certain stones could help them find the sun, and that was enough. They took that knowledge, combined it with their seafaring expertise, and accomplished something extraordinary. So the next time you're using GPS on your phone, thinking about how amazing modern technology is, take a moment to appreciate the sunstone. No satellites, no computers, no electricity, just a piece of crystal, the sky, and human ingenuity. The Vikings sailed across the Atlantic with that, and it worked. That's the strange tech they used to see without light, and honestly, I think it's cooler than GPS. Good night, everyone. And in case you've enjoyed our evening talk so much and still might be awake, here is another educational video for you.